Hi, in this video, I'll talk about a little error that people commit in doing row operations on a matrix that's 3 by 3 or larger. You have a large matrix. You successfully got a 0 in a position you want, but then when you move on to the next position, you make that 0. You end up making this first one non-zero again. So you go back and fix that, and then this one becomes non-zero. You end up sort of chasing your tail. They go 0, non-zero, back and forth. If you find yourself in that situation, this video is for you. Let's take an example. You have this system of equations, and they can be written as an augmented matrix like this. You want zeros in all these positions. So first, you get a 0 in this position in row 2. 2R1 minus R2, put it into R2. That will get you there. First row is unchanged. Second row, 2 times 1 minus 2 is 0. 2 times negative 3 is negative 6, minus 1 equals negative 7. 2 times 4 is 8, minus 1 equals 7. 2 times 14 is 28, minus 7 equals 21. And the third row is unchanged. Now we need zeros in these two positions. For the first position, we can do 3R1 plus R3. 3R1 plus R3, put it in R3. First row unchanged, second row unchanged. Third row, 3 times 1 minus negative 3 equals 0. 3 times negative 3 is negative 9, plus 3 equals negative 6. 3 times 4 is 12, plus negative 4 equals 8. 3 times 14 is 42, plus negative 22. So 42 minus 22 equals 20. So far, so good. Now you need a 0 in this position. Here's how to do it wrong. It may look like 2R1 minus R3 would get you a 0 there. First two rows unchanged. For this position, 2 times negative 3 is negative 6, minus a negative 6 equals 0. Good. Next two positions. 2 times 4 minus 8 equals 0. 2 times 14 is 28, minus 20 equals 8. That's good. But the first position, 2 times 1 minus 0 equals 2. You got your 0 here, but you lost this 0. Then you do it again, you get back your 0 here, but then you'd lose your 0 there. You'll be running around in circle. You get a 0 in one place, and then the other one becomes non-zero. That's the error I'm talking about. Let's look and see how it happened. It happened because this non-zero number 1 here, you add and subtract this non-zero with a 0, you're guaranteed to get a non-zero. That's how you lost your original 0. So that's wrong. So that's something we need to avoid doing. Let's go back and do it right. The idea is this column is done. We're done with this column. So we're not going to touch any non-zero number in this column anymore. We're not going to touch this row because it has a non-zero in this column. We go down and work with these rows only. Then no matter what we do, the first column will involve calculations with 0 only, and it stays 0. So we work with R2 and R3, not getting R1 involved at all. Numerically, this one is a little tricky because 7 and 6 are not multiples of each other. But you've done this before. It's the same skill used in making common denominator. R2 needs to be multiplied by 6, and R3 needs to be multiplied by 7 to make them both 42. or actually, one is 42 and the other is negative 42, but same skill. So 6R2 minus 7R3 going into R3. First two rows stay the same. Third row, 6 times 0 minus 7 times 0 stays a 0. 6 times negative 7 equals negative 42 minus 7 times negative 6, also negative 42, so 0. Six times 7 equals 42. 7 times 8 equals 56. 42 minus 56 equals negative 14. 6 times 21 equals 126. 7 times 20 equals 140. 126 minus 140 equals negative 14. There we go. Row echelon form. If you continue on and solve the system, you get z equals 1, y equals negative 2, and x equals 4. But the key idea in this video is when you've gotten all the zeros you need in one column, you're done with that column. If there's any row with a non-zero in that column, like R1 here, you don't use it. You use the rows that don't have a zero there, like R2. The math term is pivot. You were using this 1 to zero out the first column. Now you pivot out of that row and move here to zero out the numbers below it. All right? Hope that helps. Thanks for watching. Bye.